welcome back to another great video. So in this particular video we will be focusing on electromagnetism, right? So grade 11. This example is based on a past paper problem. This was question 7 in this case, right? So here we have a solenoid with 280 turns, and then this solenoid is moving through a magnetic field, right? Remember, it's either the magnet or the solenoid that will move. So but nonetheless there should be relative motion. One of them should move in relation to the other one, right? So now we are told that this solenoid has 280 turns, right? So let's stop there for a second. If we think about it, remember 80 turns, 280 turns means those rings. If you have a spring, if you were to count all those rings or how many times it rounds or it completes a circle, that's the ring, you would get 280 rings, right? That's another way to think about it. So if I were to draw it for you, it would look like this. I would say 1, 2, 3, 4, 5, and so on until I reach 280. So that's how it works. That's how the turns work, right? So in this case, if this was our example, since I left this one at 5, I would have 5 turns. So this piece of information right here tells us that we have N in our formula. If you remember our formula for induced EMF, N would be 280 in this case. And in this example, N would be 5, right? So imagine 280 of these rings or of these coils or loops, right? So that's what it means. Now let's continue. The rate at which the magnetic flux changes is 1.5 times 10 to the power minus 3 Webers per second, right? What does that mean? Because normally we know that the magnetic flux linkage, or in effect the change in magnetic flux, is just Weber in terms of the SI units, but in this case they added that it's actually Webers per second, right? So what does that mean? It means, if you remember our formula for EMF, we normally say E is equals to, induced EMF is equals to minus N. The minus is for the whole formula, not for the N only. Excuse me. All of this divided by T. So it's minus times N times the change in magnetic flux linkage over time. So what this means is we have this, right, being that N. However, we also have what we've been given now is this guy, Webers per second, is now equals to this whole thing. Okay, it's equals to that. Remember, sometimes we would calculate the change in magnetic flux linkage by first using the formula BA cos theta, and then we would have an initial and a final one, right? So in this case, we're just given the whole value for that delta magnetic flux over, which is delta phi over delta T, right? So that's what it is. Now we have those two pieces of information, right? We know the change in magnetic flux, the rate actually of change in magnetic flux. We know the number of turns of this solenoid, and now we are being told the area of the coil. So that means one circle out of all 280, not one, all of them have an area of 2 times 10 to the power minus 3. So all these guys, these circles, this, all of that, each and every one of them has an area of 2 times 10 to the power minus 3. Right, think of them as 280 circles, each circle, all of them having the same area, which is equals to 2 times 10 to the power minus 3. Right, so if you've seen a spring, there's no bigger ring in the spring. All of the rings are the same. Basically, a solenoid is like similar to a spring in the way it is shaped. So yeah, that's what we have, right? And then if we were to list our given information, given info, we would say N is 280 turns. We know as well that delta phi over delta t, which is our rate of change in the magnetic flux, is 1.5 times 10 to the power minus 3 webers per second. The reason we were able to tell that it's actually delta phi over delta t, or it's not only delta phi like this, the reason we were able to tell is because there was this per second, and we know that every time we have per second in an SI unit, it means whatever parameter is involved there was divided by time. For instance, velocity is a good example. Velocity has meters per second, right? This means we had distance, or displacement in the case of velocity, divided by time. Displacement is meters, time is seconds. That's why we have meters per second, which can also be written as like this. It's just meters divided by second, like this. Right, depends on what textbook you use, but normally we use this one, typically. So now we have all of that information, right? Or also we have the area. A is, we are told that it's 2 times 10 square meters, right? So this is the entire information that we have. And then let's now try to answer 7.1.1. We are asked to state Faraday's law in words. If you remember, basically Faraday's law is telling us that whenever we have a change in the magnetic field around a conductor, that will cause or that change in magnetic field or magnetic flux actually will induce an EMF in the conductor and also a current in that conductor, such that the induced EMF will then be directly proportional to the change in the magnetic flux, or the rate of change of the magnetic flux rather. And then yeah, there's no inversely proportional here. It's not like the law, was this Newton's law of second motion, for instance, where there's a parameter that's inversely proportional to the acceleration, right? So here you just leave it at directly proportional. So simply stated, the Faraday's law of electromagnetic induction states that the magnitude of the induced EMF across the ends of a conductor is directly proportional to the rate, right, to the rate of change in the magnetic flux linkage. That's it. You don't include anything else. So this is exactly how you would state it, right? So now let's check 7.1.2. We are asked to find the induced EMF, right? So in this example, or in this problem, we're not precisely concerned with the direction, but only the magnitude of the induced EMF, right? So already, if you remember, when I was introducing this problem, I stated this formula here that we usually use to find the induced EMF, right? So in this formula, from our information that we are given in the problem, we already have N, and we have the rate of change of the magnetic flux. So we can just simply substitute. So we can say that the induced EMF is equals to, we write our formula as we know it, right? Delta phi over delta t. this is minus. We have that 280 that we were given, and we have that 1.5 times 10 minus 3 that we were given. Right, someone would ask, why don't we have time and so on? Basically what this means, this 1.5 times 10 to the power minus 3, it means we've already used delta t to find the rate of change of the magnetic flux, right? So it has already been calculated for us. It's included in this value, 1.5 times 10 to the power minus 3. So we don't have to worry about it. Everything was done. So that step, we don't have to include it. So what you'll notice here, you'll get 0. Right, you get 0.42 volts. The answer will obviously be negative, right? So what this means is that, if you remember, according to Lenz's law, whenever the changing magnetic flux induces a magnetic field in the coil, I mean an EMF in the coil, as a result of the current, will also develop a magnetic field, right? But the magnetic field now, or the current, will be such that it wants to oppose the change in magnetic flux, right? So if the change in magnetic flux is increasing, say we're increasing the change in magnetic flux. So if the magnetic flux is increasing, right? Let's say it's increasing. What will happen in the solenoid, the induced EMF, right, and therefore the induced current, will then create a magnetic field that will aim to, or will try to reduce the increase in the flux. And then the opposite happens if the flux is now decreasing. So now the field that is created by induced EMF in the solenoid will try to maintain the flux, right, and not increase it. So when the flux decreases, the induced EMF created in the conductor will create a field that will try to maintain this magnetic flux. So basically what this means is that Lenz's law, this is actually a physical interpretation of what that law says. It's physically meaningful to have the negative sign, but you might find that in other textbooks or in other people, they prefer to just write this as a positive value, right? Even if you leave it as negative, even if you write it as positive, it's fine. Both are actually correct. It's just an indication of the direction of the EMF, right? So if you have a sign, it's indicating something. If you have a positive value, it's also indicating something, right? So that's one thing I want you to note. For this example, I think since they didn't specify that we must find direction or anything, we can leave our answer as positive 0.42 volts, because we are merely looking for the magnitude of the induced EMF, right? So just as a rule of thumb, it's always like that. If the changing magnetic flux is increasing, now the induced EMF will create a field in a solenoid that will aim to reduce that, right? Or to reduce the increase in the magnetic flux. And if the opposite happens, where now the flux is decreasing, the induced EMF will create a field that will try to maintain the flux, right? So that's the key distinction there. So that's why even in this formula, we always put negative here next to the formula. And that negative simply means that the induced EMF will always drive current in a direction such that the magnetic field that it produces will oppose the change in magnetic flux through the coil or the solenoid in this case. So in our example, which is the one we have in our context, right, it basically means that now since our coil is moving through a field, right, the flux is changing. Now the negative sign, which is this one, it tells us that the induced current will flow in a direction that resists that change, right? So that's basically what it means. In this case, we don't know whether it's increasing or decreasing, but whatever change is happening, this means that the induced current will flow in a direction that resists that change. All right, so I keep repeating the same thing, but I hope it drives the point across. Now, the strength of the magnetic field in 7.1.3 is required. I said we'll leave this as positive. So let's check it out. If you remember, we said the strength of the magnetic field, also called the magnetic field density, magnetic field density, right, is given by our symbol B, right, and it's measured in Tesla. So here we are required to find that strength, but let's understand the concept behind this problem. So first of all, we are told that a solenoid with 280 turns moves through a magnetic field. So here we are not told what happens as it moves. Was it first outside, or initially it was just inside the magnetic field, stationary, and then we started moving it? And then the rate at which the magnetic flux changes, we are told. The area of the coil, we are told. But another key thing that we are not told is the angle of the magnetic field lines relative to the surface area of the coil. Or sometimes, or most times actually, we measure it relative to the normal of the coil. Right, so let's check what we can do. Right, so we can tackle 7.1.3 in one of two ways. One, we can either assume that initially the coil was outside the magnetic field, and then it was then driven inside the magnetic field, and then only there did it experience a magnetic field or a change in magnetic flux, right? So if it was initially outside the magnetic field, first let's say we assume, right, so if we assume that it was initially outside the magnetic field, we'll just say the initial magnetic field strength, or the initial strength of the magnetic field, is 0 Tesla, right? Now it means the question is asking for the final one, when it was inside the magnetic field and it's being moved inside the magnetic field, right? So that's one way to look at it. The reason we have to know the initial and the final magnetic field is because if we check our question, it seems like the magnetic field is the only variable that's changing. Because remember, the only way we can find our magnetic field is through this formula. Phi is equals to B A cos theta. But the area is constant. Theta is constant. We are not told that it's changing. So this, we know for a fact that it is changing. Right, so the reason we have to think of it as changing is because this formula only has phi as just a parameter, but now we are given phi as delta phi. So it means one of these guys has to have a delta in it as well, because phi will have final minus initial, right? So we'll have final. For any delta, it means you'll have final minus initial, right? So that's one thing. And if you remember, this would mean now our B, we would have BF A cos theta minus BI A cos theta. BF being the final magnetic field density, BI being the initial magnetic field density. So that's what we are essentially doing, right? So with regards to theta, we said we will assume that theta is constant. Theta is 0, right? So basically we are assuming that the magnetic field lines are directly perpendicular to the face of the coil. So let me show you what that means. Or they are at an angle of 0 degrees when compared to the normal, which is the usual explanation or the usual convention we use. So that's our second assumption. With more practice, you wouldn't even think of these as much. So what would normally happen is you would make these assumptions by virtue of you understanding electromagnetism. With more practice, you don't have to even think that much about them. So, but nonetheless, you will understand. So we have to also assume, right? So we assume that the field lines are perpendicular to the surface area of the coil, which means the angle between the field lines and the normal is 0. What that looks like is, if let's say we take this as our coil, right? This is our coil. It means now, remember, the normal is usually just an imaginary line that's perpendicular to the coil, like this. Okay, let me draw it as a solid line. This is our normal. It's a line that's perpendicular to the coil. This is our normal. Now, theta is the angle between this line and our field lines. So sometimes you find that the field line is like this. The magnetic field line is like this. And then there's this angle between the field line and the normal. So we would be given, sometimes it's 30 degrees, sometimes it's whatever. But in this case, we are not told. So we assume that this angle is 0, which means the field lines are exactly parallel to the normal, but perpendicular to our coil, like this. So it means here it would run on top, like that, parallel, like that, like that. So these are my field lines. And then the black line would be my coil. Right, so that's what it means. Okay, our assumption. So we can continue now. We can continue and then we can solve. So let's continue from here. BF is what we're looking for. A, we are told, is 2 times 10 to the power minus 3. So if you check here, you could have done it mathematically and said, well, I can factor out A cos theta. Therefore, I would have BF minus BI times A cos theta. It's fine. You could have done it like that, but let's just continue in this fashion. And then we said theta is 0. So we'll have cos 0 minus, we said BI is 0 because we assume that the coil was initially outside the magnetic field. We have area. Area is 2 times 10 to the power minus 3. And then we have cos theta, which theta is 0. Right. And we are given, okay, let's write this guy, the change in the magnetic flux linkage to be 1.5 times 10 to the minus 3. Right? We know that any number multiplied by 0 is simply 0. So this whole thing will go away. Okay? So we will be left with 1.5 times 10 to the minus 3 is equals to BF times 10 to the minus 3. BF times 2 times 10 to the minus 3. And then from here, you can divide both sides by 2 times 10 to the minus 3. 2 times 10 to the minus 3. Then you can find that your BF is simply 0.75 Tesla. So that's our answer. That's our BF, or that's our B. You'll find that some people will just leave it as B is 0.75. Right. So in another way that you would have done it is you would just assume that this thing is in a uniform field. So it doesn't matter at which point the solenoid is at, as long as it's inside the field, our change in magnetic flux will be the same, right? And therefore B will just be a constant value. And then you'll have times A times cos theta, like this. And then from here, you'd have simply subbed in your values, I mean, cos theta is 0, and then you'd have 1.5 like this, and then you would solve for B, right? That's another way to look at it. So I took the longer route because it's easier to understand for most people, right? So that's what we have so far, and then this is how you do 7.1.3. Now let's go to 7.1.4. We are asked to find the current in the coil if the resistance of the coil is 2 ohms, right? So we are given R. Remember, EMF is simply voltage, since most people are used to that lingo or terminology, right? So what we're saying here is we are given that R is 2 ohms, right? Now, if R is 2 ohms and we're asked to find the current in the coil, if the resistance of the coil is 2 ohms, we know that from our triangle, from the guys that use a triangle, with V, with I, with R. So in this case, they are asking us to find I. So a shade of I, and we know that I should be V over R, if you remember how to use the triangle. And we know that V, since in this case we are dealing with induced EMF, we use E, induced EMF, over R, right? That's our V. So from here, we can simply substitute our value. We have 0.42 over R, which is 2 ohms, and then this should be 0.21 amps, right? So that's how you would tackle 7.1.4. It's a simple Ohm's law question, right? They just integrated it into our electromagnetism chapter or problem. So this brings us to the end of this video. Thank you very much. I will catch you on our next video.